The process of measuring distances in space involves complex techniques, including using nearby stars and cross-checking their distances based on the brightness and behavior of their light. This is often done by observing how the light from these stars and supernovae shifts toward longer, redder wavelengths due to the expansion of the universe. By studying this redshift, astronomers can precisely estimate the rate of cosmic expansion, known as the Hubble constant. In 2019, a team led by Reese used the Hubble Space Telescope to observe the Large Magellanic Cloud, one of the Milky Way's closest neighbors. Their findings suggested a faster rate of expansion, approximately 74 kilometers per second per megaparsec, compared to previous estimates. However, there were challenges in the accuracy of these measurements, particularly in crowded regions of space, where stars and galaxies could obscure each other, leading some to question the validity of these results. When the James Webb Space Telescope, JWST, launched in December 2021, it was poised to either confirm or resolve this discrepancy. With a much larger mirror, 2.4 meters across compared to Hubble's 2.4 meters, JWST can observe objects that are 10 times fainter than those detectable by Hubble and can see deeper into the infrared spectrum, providing a broader view of the universe. JWST's measurements of the galaxy NGC 4258, using type Ia supernovae as a standard candle, confirmed a similar expansion rate of 73 kilometers per second per megaparsec, aligning closely with previous findings. Other methods, including those using the brightest red giant stars and gravitational lensing, also return values around 70 kilometers per second per megaparsec, providing consistent results. However, the Hubble tension, the difference between early universe measurements and current ones, remains unresolved, prompting speculation among astronomers about potential explanations. According to Ryan Keating from the University of California, Merced, the temperature of the cosmic microwave background, CMB, is now measured with 1% accuracy, and the error margin for distances is narrowing. Although the discrepancy of just a few kilometers per second might seem small, it's unlikely to be a random error. As cosmologists grapple with this tension, three possible explanations are being considered: measurement errors, new physics, or a combination of both. The most straightforward hypothesis is that dark energy behaves differently today than it did in the early universe. If dark energy was once more powerful and then diminished, it would make the early universe appear smaller, thus increasing the measured expansion rate. Other theories suggest that dark energy could come in two forms or that dark matter might interact with light, but these ideas introduce further complexities that require more evidence. Beyond this, James Webb is also challenging our understanding of the early universe. Its advanced imaging technology allows it to look further back in time than any previous telescope, revealing galaxies that formed just 300 million years after the Big Bang. These early galaxies appear far more massive and advanced than current models predict, with some showing heavy elements from earlier generations of stars and massive black holes already forming. This raises fundamental questions about the basics of cosmology. The universe began approximately 13.8 billion years ago in a hot, dense state, and it expanded rapidly in the moments after the Big Bang. Measurements of the cosmic microwave background, CMB, are one way to estimate the expansion rate in the early universe, while observations of stars, supernovae, and other cosmic phenomena offer a different method. The current measurements, which are based on these latter methods, indicate a faster expansion rate than expected from early universe observations. The Hubble tension suggests that there may be discrepancies between our current understanding and the true nature of cosmic expansion. James Webb's data, with its greater precision, confirms this faster rate of expansion and challenges our models, especially the lambda cold dark matter, lambda CDM model, which is the standard cosmological model. This tension forces astronomers to reconsider how they interpret the universe and what additional factors may be at play. James Webb's observations also shed light on the nature of early galaxies, which appear far more evolved than anticipated. These findings challenge existing models of galaxy formation and evolution, suggesting that our understanding of the universe's early stages may need significant revision. In conclusion, the new data from the James Webb Space Telescope has opened new avenues for understanding cosmology and the expansion of the universe. It highlights the need for further research and a potential rethinking of the theories that have shaped our understanding of the cosmos. As more observations are made, they may offer deeper insights into the mysteries of the universe, pushing the boundaries of our knowledge even further. There appears to be a fundamental issue in our understanding of the universe's expansion, with cosmology seemingly at an impasse regarding one of its most essential questions. How fast is the universe actually growing? For over a decade, two methods of measuring this expansion have yielded conflicting results. Observations of the present universe suggest the rate of expansion, known as the Hubble constant, is about 9% faster than predicted based on early universe data. Scientists had hoped the James Webb Space Telescope, the most advanced telescope ever built, would help resolve this discrepancy. However, instead of providing clarity, it has only deepened the mystery with highly precise new measurements that challenge the standard model of cosmology. This has led to a renewed debate among physicists about whether the current 40-year-old theory needs a major revision or even replacement. This surprising turn of events raises the question: what is it that we fundamentally misunderstand about the universe? Let's delve into the latest deep space images from the James Webb Telescope, which confirm that something is indeed amiss in our comprehension of the cosmos. According to current understanding, the universe began with a Big Bang, where space, time, mass, and energy came into existence in a single fleeting moment. In its infancy, the universe was a hot, dense plasma of particles, matter and antimatter, that annihilated each other upon contact. In theory, this should have led to the total destruction of matter. However, some unknown imbalance allowed more matter than antimatter to form, preventing the universe from collapsing in on itself. As the universe expanded, gravity began to compress pockets of plasma, heating and squeezing the matter so that sound waves, known as baryon-acoustic oscillations, rippled across the plasma's surface. Meanwhile, the universe's high-energy, dense content stretched the fabric of spacetime, causing a small amount of mass to escape the early universe's singularity. As space continued to expand, ordinary matter, which interacts with light, began to clump together around invisible dark matter, forming the first galaxies, interconnected by a vast cosmic web. As the universe aged, its energy density and rate of expansion decreased, until about 5 billion years ago, when a mysterious force, dark energy, began to accelerate the expansion again. The simplest explanation for dark energy is that it is a constant, inflationary force embedded in spacetime, a concept first introduced by Einstein as the cosmological constant lambda. As the universe expanded, the density of regular matter decreased, while the density of dark energy remained constant, making dark energy the dominant contributor to the universe's expansion. This understanding is encapsulated in the lambda cold dark matter, lambda CDM, model of cosmology, which has guided our understanding of the universe's evolution and predicted its eventual end in a big freeze, when the universe becomes too diffuse to support matter. However, significant problems arise when we attempt to measure the expansion rate, as the results appear inconsistent. Despite extensive efforts, astronomers have been unable to fully explain what dark matter and dark energy are. According to astrophysicist Ofer Lahav of University College London, the widely accepted cosmological model consists of 5% normal matter, 25% cold dark matter, and 70% dark energy. But the problem lies in our lack of understanding of dark matter and dark energy. Even more concerning is the discovery of a Hubble tension, which suggests that the universe is expanding at different rates depending on the method used to measure it. One technique involves observing the cosmic microwave background, CMB, the residual heat from the Big Bang that permeates the universe. Measurements of the CMB by the European Space Agency's Planck satellite between 2009 and 2013 suggested a Hubble constant of around 67 km per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years, a galaxy is from us. It is moving away at a speed of 67 km per second. This rate increases for galaxies farther away, and at distances beyond 4,175 megaparsecs, the recession speed exceeds the speed of light. A second method for measuring the expansion rate involves the observation of Cepheid variables, pulsating stars whose brightness fluctuates at regular intervals. By comparing the apparent brightness of these stars with their intrinsic luminosity, astronomers can determine their distance and, from there, calculate the rate of expansion. This method has been fundamental in creating what's known as a cosmic distance ladder, helping astronomers measure large-scale distances across the universe. However, despite these two methods being independent, they have yielded conflicting results, with one suggesting a faster rate of expansion than the other. This discrepancy, known as the Hubble tension, raises questions about the accuracy of our understanding of the universe's evolution. Could the standard cosmological model be incomplete or fundamentally flawed? In summary, while the James Webb Space Telescope has provided unprecedented views of the distant universe, it has also deepened our understanding of the expansion problem, challenging our current models and opening the door to new theories. The mystery of dark matter, dark energy, and the true rate of the universe's expansion remains unsolved, signaling that our cosmological theories may need a major overhaul.